Well, it's 2 minutes after the hour, and we'll probably get this webinar underway. This is the third of our 3 webinars on working with the Vsoft products, and we're very happy to be able to bring you these 3 webinars. Hope you've enjoyed them. Today we'll be talking about Microwave Pro 2. John Gray, of course, will be your presenter. I have a few things to present myself. So without further ado, I should say that I don't think I've given my name, but I think you all know it. I'm Doug Vernier. So I'll send it over to John to begin a general overview of Microwave Pro 2. So John, take it away.
All right, thanks, Doug. Hope everybody can hear me okay. Just let me know if you can't. I think what I'm going to do today is start off with just a little general discussion about the microwave coordination in general. Some of you who are watching may be fairly familiar with microwave. Others of you may not. It's a little bit different than your standard broadcast stuff, and you got to think about it a little bit differently. So I kind of want to go through some of the basics, and then we'll get into the program and how it deals with the coordination process. So we'll start there. If you guys have any questions, feel free to chime in or put them in the chat window, and I'll try to address them. All right, so here we are. So on a microwave setup, you're looking at point-to-point paths generally. So what I've got here is a diagram of a typical possible interference situation. And so say you're working on a new proposed path, and I've labeled this kind of the same way that it is labeled in the TSB 10F document, where these letters, that's kind of where these come from. So your new proposed path is going to be D will be your transmit site, and E is the receiver site for your proposed path. And then in this example, say we're going to look at protecting the other existing paths out there. So your existing paths, A will be their transmit site and B will be their receive site. So you're going to have, in this situation, an interference path from your transmitter D over to their receiver that's located at B. So this is kind of the typical generic arrangement you might have in terms of a single, let's look at interference at this point. So what essentially we're going to do is we're going to want to calculate the C to I ratio, the carrier to interference ratio at the receive point of the existing path to see if interference exists. And then we're going to compare that C over I that we've calculated to a C over I objective, which is essentially, at what level do we cause unacceptable interference. So generally, you want your calculated C to I to be greater than your interference objective. So that's sort of some words that I'll be using throughout the talk today. So I just kind of wanted to run that down. So how do we calculate this C to I ratio? Basically, what we're going to look at is our C, which is going to be our desired signal level. The way we calculate, we take the power output at A, and this is kind of all in dB, so we're adding here, and then we're adding that to the gain of our antenna that we have at site A, plus the gain of our antenna at site B, minus the path loss from this path A to B. Typically, your protected paths, there's only going to be the free space path loss. You generally shouldn't have any obstruction loss on a working microwave path. So essentially what we're talking about in terms of the C is the free space path loss. And then our I, our interfering path, we're going to take our power at our transmitter at D plus the gain of that antenna that's at site D, and then plus the gain at B again. And then we're going to take out the discrimination attenuation, basically, from both of those. So on these microwave paths, what you've got is a highly directional, high gain antenna. So in this case, like our D to E, our D antenna is going to be pointing directly at E. So as we get off axis in this angle here, the signal will be fairly attenuated. And so we need to take that out in our calculation. And then also at point B, B is going to have its antenna pointed directly at site A. So because of the angle difference you've got there, you're also going to have your discrimination due to the antenna pattern at point B. And then, of course, you've got your path loss at dB. So when you combine these, the C over I, basically your gain at the receive site cancels out, and then the rest of these all kind of get together. And so, this is fairly straightforward. Obviously, the C over I ratio is going to be lower the higher your interfering transmitter power is. That makes sense. And then discrimination, you want to have as much discrimination as possible. Your C over I ratio will be lower the more antenna discrimination you have there. And then, of course, the more path loss in this interfering path, the better in terms of trying to eliminate interference. So that's sort of the basic calculation that we're doing here to determine our interference levels, and we'll see this when we get into the program, how that looks in the interface. The next thing, let me go back here, just talk about this for a second too. At all these sites, at site A, there's going to be an antenna. At site B, there's going to be an antenna. At D, there's going to be one. At E, there's going to be one. And with these microwave paths, generally, the way the antennas are specified is you have patterns based on the polarity that you are configured to use. So there will be one pattern, an antenna will have one pattern if you're using the vertical polarization. Polarity is not right, the polarization. So you will have one pattern for the vertical polarization and one pattern if you're using the same antenna in a horizontally polarized manner, then the pattern will be slightly different. So on this next screen, I've kind of got a view of this, and this will come up in terms of our path configuration. We're going to specify two antennas, one for the transmit site and one for the receive site, and each antenna is going to have 4 different patterns associated with it. And so those patterns, the HH pattern, I've got it kind of defined up here at the top. The HH will be the horizontally polarized port response to a horizontally polarized signal. And HV is the horizontal polarized port to a vertically polarized signal. So essentially, when you're looking at your patterns here, it's going to matter whether or not you have the same polarization as the path you're trying to protect, or if you have the opposite polarization, and different patterns will be used based on that. So and the same antenna can have, if it's set up in the horizontally polarized manner, you will have this pattern will be your horizontal radiation pattern, and if it's set up in the vertically polarized manner, it'll have this. So you can see those patterns are different. And then over here on the other side, we've got our cross-polarized patterns, which are used in terms of the receiving end. When you've got a receiving antenna, if it's set up in the horizontal polarized mode and the incoming interfering signal is a vertically polarized signal, then you will use this pattern here. And if you're set up in the vertically polarized mode and the interfering signal is horizontally polarized, it will use this pattern in terms of determining how much discrimination you have at the different angles. And I will show you a little bit more about how that works when we get into the program. The last little wrinkle here before we get to looking at stuff is it's not exactly as simple as you just have 2 paths, because there's also this second interference path, which is going to be the existing path that's out there that you're going to pull out of the database, may be causing interference to your proposed path. And so you want to look at that as well. So essentially, in every relationship, we actually have two protections that we need to look at instead of just one. And that makes it a little more complicated. So in terms of, it's easy to get turned around in terms of, what are you looking at and all this. So you kind of have to keep this clear in your head. And I find going back to a picture kind of like what I have on the screen right now is sometimes helpful just to keep your head straight. And like I say, in the program, there are places where we label it, and we use this A, B, and DE labeling to match up with that. So as a note then, what you're going to see in the program is there will also be things labeled as your C over I out and your margin out. Whereas in the margins that we're going to look at, that's essentially just the difference between your calculated C over I and your C over I objective. So if you've got negative margin, that indicates that your C over I is not high enough. And there may be interference there. So when you see this, if you see, C over I out or margin out, the out is with respect to, all this stuff is with respect to your proposed path. So the out is going to be the outgoing interference, in the sense the interference that you're causing to somebody else. And you also see things labeled as C over I in and margin in, and that's essentially your incoming interference. That's interference that another path out there is going to be causing to your reference station or your reference path. So that's essentially what, when the program's doing its calculations in these tables that it generates, this is essentially what it's telling us, is what these values are for in and out for our C over I and our margin. So the next step here is we're going to go ahead and go to the program. Oh. And to do that, there it is. All right, so here's our program. When we load it up, it's kind of like Probe in that we get sort of a start screen, and this is sort of new in Microwave Pro 2, where you've got the option to create a new study or go to the website or load a recent file. Obviously, you can just click on any of those to do what you need to do. Of course, we're going to go ahead and create a new study. When you do that, you've got three options. You've got the single path analysis, the frequency search, and the point search. Now, our single path analysis is where we're going to enter one reference path, and that's going to be, and we're going to look at the interference that one single path causes to other paths and the path that the other paths in the area cause to that one single path. And that will tell us, whether or not that particular path is going to have, interference issues or will meet the coordination guidelines and such. The frequency search is essentially just a whole bunch of single path analysis. So on that, you're going to specify a reference path, and it will go through and do the single path analysis on a bunch of different frequencies and polarizations, and then you can kind of rank the results and use the one that, find the frequency that is going to work best for your particular situation. And then the last one is our point search, which is just a simple study that allows you to identify a point location, latitude, longitude, and will show you all of the microwave paths that come near that location within a user definable distance. So we'll get into looking at all these today, but that's the three options. So single path analysis is sort of the heart of the program, and that's what we want to look at first. So when you go to run a single path analysis, it's going to come up with the path editing window. And this is the window you will use to enter the path data and essentially define all the variables for your particular path that you're considering. Some of you that are familiar with Microwave Pro 1 but haven't used 2 yet, this is something new up here at the top. It's got a selection for the path type. You can do a one-way path, in which case you're just going to specify that, or you can actually tell it to do a two-way path, in which case you've got, a forward path on one frequency, and then you're going to have a return path on a second frequency. And so this allows you to toggle between the forward and return path using these buttons up here. So just to talk a little bit about the data entry, the stuff up here at the top, you've got your identification. That's essentially just your call sign, the ULS file number that'll come out of the database when we pull that out of the database. You specify an emission designator. We'll talk a little bit about that more, and then the ULS system ID is just another thing that comes out of the ULS database. Now, on the left-hand column here is where you're going to specify your transmit technical details, latitude, longitude, height, elevation, frequency, polarization, either horizontal or vertical, and then your EIRP. So when you've got your transmit site defined, and then the column over here on the right defines your receive site, once again, latitude, longitude, height, and elevation. That's your basic definitions. Down here at the bottom, you'll notice there's a load from database button. If we click on this, it's going to pull up our database search function. And this is similar to our other programs, where you can put in just about any search string. You can put in a city, or you can put in a call sign, or you can put in something that will appear, or something that exists in the record, and it will return all the records that match that. So for example, I'm just going to type in Des Moines, hit enter, and it's going to go ahead and search. And you'll notice up here it's got this search databases. We can search the license database, that's the ULS license database, the applications, ULS applications database, or the My database. The program has the ability to define your own database where you can put in stations that may not exist, or paths that may not exist in the ULS database, and you have the option to include those in your search results here. So the point here is we're just going to load a station. All of these headers at the top of the column, if you click on them, it will sort by whatever header you click on. So if I click on Freq, it'll sort by frequency. And if you hover your mouse over any of these, it'll give you some more details on some of these. This one's kind of sparse, but RX site is receiver site name, EM is emission designator. So if you're looking for a little more information, you can hover your mouse up there and it'll show you. So here's a list of all the records where it matched the string Des Moines in them. I'm just going to scroll down the list here. We'll pick, here's one out of the license database. We'll go ahead and pick this one. You essentially can pick the record you want, hit OK, and now it's loaded all of the information from that ULS record into our editor here. So, we didn't have to type all this stuff in. It pulled it straight out of the database. These from ref and to ref buttons, just while I'm thinking about it, I'll mention those are the VSoft reference file. You can use that to store some limited information. In this particular situation, it'll just store the coordinates. So if you had in another program or in another box in this program a set of coordinates, you could use this to ref to save that to the reference file, and then you could use the from ref button to pull it back in. It's kind of like a clipboard for coordinates. In some cases it'll do more than just the coordinates, but in this one that's what it does. So we filled in our transmit site and our receive site. There are other things that it loads out of the database. We've got this other details, which it also has, transmit on the left and receive on the right. These are various information about the location name and the address, tower registration number, just general information that could be handy. This is also where it has the parent station stored, and it pulls that out of the ULS as well, the call sign of the broadcast parent and the information about that. And then down here, the radio service code. And if you drop this down, it'll show you what all these codes mean. There are some places in the program where it just shows the code, and you can come back into here to find out what they are. And then also it fills in this contact info tab, which is essentially the licensee and the licensee contact information that it pulled out of the ULS. And it will use this later when we get into the PCN process to determine what where we should send letters and such for the PCN process. The next two tabs that are kind of important here, this transmit antenna and receive antenna, and I told you that every path is going to have two different antennas, or they can have. A lot of times they'll use the same type of antenna, but there are cases where there'll actually be different antennas at the transmit site and receive site. So the program allows you to specify those independently. One of the things about the program that's important to understand is that the antenna pattern data is not stored in the ULS. It does not have the actual patterns themselves. All it has is this manufacturer and model number, which can make it kind of a challenge sometimes, because the program will attempt to match these things up, but in an effort to prevent false positives and stuff, it doesn't, especially when it comes to the model number. The manufacturer name, sometimes it'll substitute what's in the database for something that matches what's in our pattern library, and but for the model, it pretty much has to match exactly. And if it doesn't, what happens is the program will assign a kind of generic pattern based on, well, in this case, it'll be based on the frequency of the station you loaded. So this one was a 947 megahertz station. So it's loaded the generic FCC pattern that sort of matches that part of the frequency band. But we'll see here that it actually indicates, the Mark P9A72G is the antenna to use here. And for this one, it's the same for both the transmit and receive. So at this point, when setting up our study, it's sort of important that we have the right antenna set up for the reference station. So we want to make sure we go in and load the appropriate pattern. And you can kind of tell by looking at these that it's, this is not the pattern from the database. When you see this sort of stair step type of thing, that's one of these generic FCC type of mask patterns. So if we go down here to the bottom, we've got some options. There's load all patterns from a file. This will, the NSMA has a couple of standard formats that they specify this kind of data be stored in, and it actually stores all 4 patterns in one file. So if you happen to have an NSMA compatible file for the antenna you're looking for, you can use this button and pull that in from that file. The next button here is this load from pattern library, and this is built into the program. We have a reasonably comprehensive library of antenna patterns. So the way this works is you've got your manufacturer on one side and then the model numbers on the other. So in this case, we're looking for this Mark 72G. So we'll click on Mark, and you see the way that these are specified in here. It's, because of this asterisk on here, it didn't exactly match that up, so it wasn't able to pull in the pattern. But we can just select this and hit OK. And then this next window that comes up is the beam width number. The one thing about these NSMA files is they've only got one beam width value, and typically when you look at the data, the beam width for the horizontal polarization and the vertical polarization can be slightly different. So depending on whether or not you've selected horizontal or vertical polarization and all that, the beam width that it tries to pull in, so it'll tell you that the value that's in the file is 12.5, and then it also shows here, looking at the pattern, it calculated that it should be 12.5 for both the HH and the VV. So in this case, they're all the same, so we can just use the value from here. In some cases, if the number that's in the file doesn't match the calculated, you may want to choose to use the calculated value, or you can enter whatever value. The one thing to note about this beam width value is it's used here, but this is really just for show. When it does any kind of calculations or anything, it's actually using the pattern data. And so, even though there's a number specified here, it'll show that on some of the reports and stuff like the path information, but it doesn't actually use that in the calculations. The gain, however, it does use in the calculations, and this was pulled from the ULS database. So, and the tilt up here is also one of these things that is just, it is not used in the calculations, it's just there for show. It will come up on some of the reports. And if you use this calc button, it'll actually use your, I'll click that here and see what it says, so 0.12. That's actually going to use the coordinates from this page, coordinates and heights, and determine what the actual tilt in the antenna is going to be to get those to match up. So now we could go into this receive antenna and go back to the pattern library and pull this out of here, but since it's using the same for the transmit, what we can actually do, the easy way to do it would be to go back to the transmit tab. There's this button here that says copy to receive. And if you click on that, you'll see now when we go over to our receive antenna, it just copied that data over from the other screen. So that's all we need to do to get the right pattern in there. The last button on here, I just mentioned it, is the Save Patterns button, and that will actually save this data to one of these, I believe it doesn't say the file type, but I believe it's one of the NSMA formats. You can actually dump the data out into that if you needed to save it for later. And the last note I would have on here is these patterns. We've loaded the data. If you had a situation where maybe you have a spec sheet but you don't really have a file, you can actually manually set these up, and so any of these you can just click on them and it brings us into our discrimination pattern editor, which this can be used for a couple things. One, you can use this just to kind of look up what a specific value is if you wanted to know, and also any of these you can click on them and change the value, edit them. If you were typing a new one in from scratch, you would hit this clear pattern button, and then you would use add point, and you'd put in the angle and the value that you read off the graph, and it has an option to add the symmetric point. I'm going to cancel that because I don't want to keep that change, but so it has the full ability. You can specify all of these patterns in the program if you don't have a file. And this load and save will save just this one individual pattern to a file. And the last option is print. It has a basic kind of printing feature where you can print that single pattern out. So that's roughly how the discrimination patterns are specified and work. And I guess the one other thing I would mention here is that the patterns are sort of specified in terms of gain, in that the numbers are all negative. But when you see this in the program, it's going to list them in terms of attenuation. So like at this 12 degree, it'll show that as a plus 10 in the program because it's 10 dB of attenuation. Not a big deal, but just something to be aware of. So that, I think, is a pretty good rundown of our path editor. It's fairly straightforward. I think I'm going to go ahead and just hit OK on this so we can get into the next part of it. There's a couple other features in here that I'm going to go back and talk about a little bit, but that's essentially how you set up a path or load one out of the database, as we just did. So when you hit OK on that, it's going to show our interference project setup window. This is where all the options are that kind of define what the interference project is going to look at. There's some options here for the database. You can pick, do you want to include the licensed applications or the My Records? For the license database, you can put in active, expired, and other. A lot of times you may want to, you probably want to include the expired records that are in the ULS database because it's possible that they may get renewed and you have to protect them. So it's generally you want to have at least the active and expired records considered. Down here at the bottom half of this is our sort of study parameters. We specify our default C over I objectives. The way this works, so when it comes to calculating what your C over I objective should be, that can actually get somewhat involved, and it has to do with the bandwidth of the signal you're using and the modulation scheme and the receivers themselves. And so there really isn't enough information in the ULS data to really fully calculate what these C over I objectives should be. So generally, you will have sort of a generic or just general, all-purpose value that it'll use. So typically, the 65 dB is used for co-channel, which means that your interfering signal needs to be 65 dB below your protected. And then our first adjacent, usually it uses a 30 dB, sort of a standard, and of course you can change these. One of the things, and so that's the co-channel is essentially stations where they're on the same frequency or have overlapping channel bandwidths, and first adjacent is where they're more than one channel bandwidth away, but less than two. And so in Microwave Pro 1, you just specified these, and it would assign everything that it determined was a co-channel it used 65 dB for, everything that it determined was first adjacent it used 30 dB for. In Microwave Pro 2, we've added an algorithm, and there's a checkbox here that will turn that on. It says adjust C over I objectives for frequency separation and bandwidth. What that will do is you will run into a lot of situations where there will be stations that are offset by some amount that's less than a full channel bandwidth, or you'll have stations where the one station will be a 500 kilohertz bandwidth and the other will be 300. And this will actually make an attempt to adjust these C over I ratios appropriately to deal with kind of the special cases where you're not exactly a co-channel or exactly a first adjacent. And so that has one interesting effect is in that if you're just slightly offset in frequency by far less than a full channel, you will actually that will drive your C over I objective up. So you could get up to 70, 75 dB if you've got just a slightly offset co-channel, slightly offset from the same frequency. And then as you move away in frequency, then your objective will go down. And so in between sort of the co-channel, it'll fade sort of from the 65 down to 30 as you move away, and then as you get more than a full channel separation apart, it will go down below 30. So like I said, that's a new option, and so that's something different where you'll actually see every path in the study has a different C over I objective. Our next option here, it says consider obstruction loss 4, and it's got two options: protected paths and interfering paths. Typically, with protected paths, in general, there shouldn't be any obstruction loss. They should be, direct line of sight paths. However, in the ULS, there are some paths where, and it may just be because of bad data in the ULS, or it may, I don't know exactly why else this would happen, but you will find paths where there's a fair amount of obstruction loss on a protected path. And so if you have this box checked, it's going to put that in there, which means that it's going to see the signal levels at the receive point of those protected paths to be extremely low, and it's going to make them, you won't really be able to protect them because or you'll have to way over protect them. So if you uncheck this box, it's going to assume that a path that's in the database is a clear path and doesn't have any obstruction loss. It'll still include the free space loss, but it doesn't, even if it detects that there's obstruction loss, it won't include that in the calculations. The next option is this interfering paths. Typically, if there is obstruction on the interfering path, you do want to consider that. The only case where you may not want to is if you wanted to be ultra conservative and just consider free space. If you only one to consider the free space path loss and no obstruction losses, then you could uncheck this box and it would run the calculations in that manner. And then the last option here, this only include co-channel and first adjacent stations. This is sort of a throwback to an older version of the program. Generally, you're always going to want to have that on. If you uncheck that, it may load other frequencies that are far away from your reference frequency. That's really just kind of there to be backward compatible with the older version of the program. Our next other options here, we have edit generic pattern. So this is, as I was talking about before with these discrimination patterns, the ULS database does not have the pattern data. And a lot of times it won't have even the make and model. It'll just be blank. So if you try and run the study and not considering any antenna in that case, you're going to find a whole bunch of violations because these are all highly directional systems, and it just doesn't make any sense to consider like an omnidirectional antenna on them. So what the generic pattern does is it allows us to, in the cases where either the antenna isn't specified or the program is unable to link the specified antenna with one in the pattern library, it will apply the generic pattern, and it kind of automatically decides what that should be based on the frequency of your reference link. So if we click on here, it's going to have the same kind of generic, this 941 to 944 FCC, 101.115 pattern for this. And so, it'll automatically do that. If you wanted to override that and have it use, some other pattern, you could certainly load that here, and that's what it'll use in the study for the generic pattern case. And then the next button is our propagation settings button. I'll click on that so you can see what it looks like, but I'm going to come back to this and talk about it in a little bit more depth, but this is basically just the settings that it uses when it's doing the propagation calculations. So that's essentially how we set up the study. So I'm going to go ahead and hit OK. Now, when you hit OK on this, it's going to go out and search the ULS database and find all of the, paths that have a co-channel / first adjacent frequency type relationship with the reference path that we put in. It takes a little while because there's a lot of records, and essentially what it does is it searches through the database, or a shortened version of the database that just contains the coordinates and the frequencies and such, and determines which records it needs to load. And then at the end where it says building records, it's actually pulling in the other data, like the contact info and the various other data that's associated with the paths that it didn't load on the first pass, basically. All right, and then the final stage is calculating. It's actually going to generate terrain profiles for all of our protected and interfering paths, and then in the end we're going to get a table which shows the situation. So let me explain what we're seeing here in the table. Make that a little bigger. Okay, so each row in the table represents a path that it was protecting from. It is protecting and looking at interference causes stations. So this first one, if you'll notice, it's actually the same path as our reference path. So we can actually get rid of that one, and if we just click on highlight it in the table and hit remove, it takes it off our list, so we don't have to worry about that one. So essentially what it's showing us here is our call sign of the path, the frequency that it's on, the polarization of that path. So you'll notice the one that I loaded as a reference, it has this H up here that tells us it's a horizontally polarized signal. This path is V, it's a vertically polarized signal. Next is the separation, which is the separation in terms of frequency. In this case, it's a 0, so that means we're on the exact same frequency. If we look down in the list a little, there's one here, it's 0.5, so that's, one full channel apart. So you got your frequency separation. Next is the distance, which is the distance from our transmitter of our reference station to the receive site of this particular path. Next is that service code, and then the owner column. The way this is set up, and like I say, this is one of these where if you put your mouse over thing, it'll tell you what these things mean a little bit more, give you some more info about what units it might be using or whatever. But so the owner defaults to being the parent station, which I showed you guys earlier was on that other tab. If there is no parent station specified, then it will show the owner from the contact information tab. So, most of these stations have, an FM, radio associated with them. Like this one here has something else, and if we go into our other details, you notice there are no call letters for the parent station, even though it does have some other information. But so it's pulling this entity name out of the licensee thing, and that's what it's showing in our table. So there's that one. Okay, so next we get to the actual calculation part. So C over I in, that is the C over I ratio that was calculated that is incoming to our proposed station. So in terms of looking at this WQRW212 causing interference to our proposed path, the C over I ratio that we got calculated was 42.2. All right, so the next column, C over I out, is the protection of this station in the row. So it's interference caused by our reference station to the station in the highlighted row. So those are essentially just the numbers that are calculated, and then we have to compare those to whatever our C over I objective is in order to get something useful out. In this case, it's a co-channel, so it's going to be, our C over I objective is going to be more than this probably. And you might want to ask the question, well, what C over I objective is it using? It used to be fairly simple, and if you uncheck that adjustment box, it's fairly simple where it will just, if it's a co-channel, in this case we're separated by 0 megahertz, it's going to use the 65 dB, and if it was first edition, it used 30. But since we're adjusting, that may not be the case. So if we double click on this row, it's going to take us into our editor. And if we click on this other details tab, we're going to see it is in fact using 65 dB for the C over I objective for both in and out. And the reason it's doing that is because they're obviously directly on the same frequency. And if we look at the emission designator, we'll see this is a 500K channel bandwidth, and our reference station is also 500K. So there was no adjustment that needed to be made. It's just using the fixed 65 dB ratio for that. This next column is our obstruction loss in the outgoing situation. So in terms of the path from our proposed transmitter to the path that's in this row's receive site, the obstruction loss, and you'll notice this number is negative. That is kind of a side effect of the statistical adjustment. I'm going to come back in and talk about how it determines these path loss numbers. So this is the obstruction loss out. It's kind of odd that it's negative. Usually, it'll be positive if there's any blockage there. In this case, since it's negative, there probably isn't any blockage. And then the last two columns of note here, margin in. So if these things are negative numbers, it'll highlight them in red, and that indicates that we've got a potential interference situation where the C over I objective is not met. In this case, by 22.8 dB, that's the difference between 42.2 and our 65 dB objective. And then the last column is the out, which is the interference we're causing them. So we've also got a violation there. So that's essentially how you kind of look at this table and understand what it's trying to tell you. Is all of these things where you've got a red thing is where your C over I objective is not being met. as far as why, you know, sometimes it's simply a matter of the data, and that's one of the things you kind of have to be careful with the ULS is there is a number of cases where it will be missing some data or otherwise have some sort of invalid data, and that's what our final column in here, our notes column, is really all about, is kind of identifying what is it about this particular path that might not be up to par. So if you see any that has anything in the notes column, with the exception of this ST out and STN, which I'll talk about later as well, if you see anything other than those in this notes column, then you may need to look further and make sure that you've got everything specified that needs to be. So, like for example, this one here that's blank, that means that it is everything seems to be in order. So as far as these notes, so all these are just little character codes, and as far as what do they mean, the answer is right up here at the top. If there's this little button up at the top that says notes, and if we click on that, it's going to tell us what they mean. So the top three, this AP, MY, and USR, those are just indicators that the record is not a regular license record. It either came out of the application database or it came out of the My database, or it's a USR is like a user entered record that didn't come out of any database. If it says INC over there, it means it's an incomplete data record. I see there's an INC on this. So if we go into our path editor and look at that, if we look at all the values here, those all look okay. We get over here, well, this height is shown as -999. Now that's something that the program will do to tell you that the value was not in the ULS database. So when it pulled this record out of the database, there was no number in the field where the height was supposed to be, which is, not that uncommon. The program will default it to a height, I believe it's 50 meters. If you look in the help file, there's actually a section under the methodology that says what it will default things to when it can't find them. So it still does a calculation, and it'll use an assumed value there when it can't find it. But essentially, it's warning us by having this INC here that it may have had to make some assumptions when it generated those values. So just to go back to the notes here, the GT and GR, this is telling us that either the generic transmitter or generic receiver discrimination patterns were used. That means that either there was no pattern specified or it couldn't find a match for it. That's the most common thing you will see. There's a lot of times it won't be able to match those up. And in that case, like for example for this station, if we double click on it and go to the transmit antenna tab, we see that it's a Scala PR450. Now, unfortunately, the PR450 is one of these weird deals where it's not really an antenna that was originally designed to be used in this frequency band, and people are using it anyway, and there is no pattern data that I have or that we have in our pattern library for it. So on that, you're going to have to go with the generic pattern, or perhaps try and find something else that you feel represents it. And this is the same for the receive. So that's what we have going on for that station. If we go down to the next one and look at the transmit, you see this one's blank. So this one, if we're wanting to get accurate numbers out of this, we may need to contact them and find out what they're using and put that in, or otherwise just go with an assumption. The next one here, there's another PR450, and so on. So you can kind of go through these, and you want to look at the ones that are kind of close, and if you can find the appropriate pattern for them, you want to load them. So this one here is a Mark 72. So this we actually do have something we can load from the pattern library for. So if we go in here and load, and we had loaded one of these earlier, so go ahead and pull that in. So there's the data for that. And this one for the receive site, you notice it's actually a different one. This is the Mark 96. So we'll go ahead and load that one in here as well. And you see those are two different patterns. So they're actually using a different antenna at the transmit receive site. So like, we'll take note over here, this is the WPSG 783. If I hit OK on this, it's going to go through and recalculate that. And now if you look, I changed that antenna. Before we had a negative margin up there, but now that we've put in an appropriate antenna, and it's not just using the generic default antenna, you'll notice that negative margin went away and we're actually clearing the C over I objective there. And so that's kind of, there's a little bit of a game you got to play with the missing data and all that, and it kind of, some of the bands are better than others in terms of, when you get into a lot of the Part 101 type stuff, it's a lot better about matching up the antennas, and I think the quality of the data in general is generally better there than it is in this sort of 950 BS part. But just to kind of keep going down the list here, this EM invalid emission designator. So that's, you don't see that too often, but occasionally you will. It's usually when it's missing one. And just to talk about the emission designator, because that's kind of important. When we go into our path editor, it's right up here at the top. If you click on this build button, so these emission designator codes, it's defined what these are supposed to be, but we actually have a little EM designator builder where you can go in and put in this necessary bandwidth. That's essentially your channel bandwidth. You can give it a value in hertz, kilohertz, megahertz, so on and so forth. So that's the first 4 characters of this code. Tells you what that is, and then there's other information like the modulation type of the main character, the nature of the signals, and then the type of information being transmitted. So all these have drop downs, and you can kind of see what the different values mean, and of course the program will tell you what they are. The main thing with the emission designator is you got to get this necessary bandwidth thing right, because it uses that in the determination of if a station is co-channel or first adjacent, and it uses it in making this adjustment to the C over I objective. So it's important that that be right. And any of these studies, when you're setting them up, especially if you're typing in a new path that you haven't looked at before, you got to make sure you get the emission designator right. So here's an example here of this station's frequency separation is 0, but when we double click on it and we go into our other details, we see that our C over I objective is different than the 65. And the reason for that is, if we look at this, we see this is actually not the same. This is a 300 kilohertz bandwidth signal instead of the 500K. So it's it comes up with a representation of the spectral energy density, and compared to our main signals of 500K, it will perform this adjustment based on that. So that's an example where you can go in there and look and you see it. And on some of these, like here, we've got a frequency separation of 0.125. That's far less than 500 kilohertz. So if we go in and look at the, double click on that objective there, we've got a 79 dB going one way and 64 going the other, and that has to do with the fact that it's a 250. When you get these non-matching bandwidths, that's where you'll get different values for the in and out. It compensates for that. So, yeah, so just to finish our thought on our notes here, we talked about the emission designator. This calculated receive coordinates used, that's something that also comes up in the database. I'm looking. I see one potential thing down here. This is RX1KM, which is a little different than that. But essentially what that means is our latitude and longitude may be missing. But when they're missing, there will be sometimes in the ULS it will specify an azimuth and a distance. And so if it has those and it's calculating our endpoint instead of loading the coordinates out of the ULS, it'll show this RXC, the calculated received coordinates used. If it has this RX1KM, that means, and like here's an example down here that has that. That means that in the ULS database, the latitude and longitude of the receiver weren't specified, but there was an azimuth, so you have some idea of what direction the path is, but you don't have any idea how long it is. So for this to get some calculation results out of it, it uses that azimuth and it puts in a distance of 1 kilometer. So that allows it to appropriately apply the angles involved with the discrimination patterns and such, but the receive point that it's protecting may not really be in the right place. So that's essentially what that's telling you is that, yeah, we didn't have the coordinates and we only had the azimuth when you see this RX1KM. This RCV, bad receiver coordinates, that's if there's no information at all about receiver coordinates, there's no azimuth, there's no distance, there's no coordinates, it'll give you that. So you really don't, those ones, it's kind of a who knows type of situation. And that, like I said, that comes down to the data in the ULS. You don't see that one that often, but it does come up from time to time. This next one, it says loss. It tells you the protected path has calculated obstruction loss. This goes back to something I was talking about earlier, where if you've got a protected path and it's showing a bunch of loss, and I think the loss has to be more than 3 dB for this flag to get shown. But if it's showing a bunch of loss, that's a pretty good sign that there's something wrong there. Either your heights are wrong or your coordinates are wrong or something's wrong, because you should not really have generally you should not have a microwave path that has a lot of obstruction loss. And then the last two, ST out and ST in. This comes down to another wrinkle in how the calculations are performed, and that is when it goes to calculate our C over I ratios. We talked about part of that is it looks at the path loss. Well, when you go to calculate the path loss, there's two, and this kind of comes from TSB 10F. It's outlined in there that there are two cases you want to consider. One of them is the long-term fading case, which is going to be where you have, outages that are persistent, and last for a long time. And so for that, the recommendation, and that kind of comes down to our propagation settings. They suggest when you run your propagation model, you look at it 20% of the time kind of figure. So you want to, so you're showing the path loss when 20% of the time the path loss is going to be more than the specified. Well, it's not the path. The attenuation will. It's easy to get turned around on this. 20% of the time, the attenuation will be less than what is specified, and so the short-term case, which is the second case that you should look at, is where these sort of due to atmospheric conditions and ducting and all this, you may have situations where you'll have short-term, very short outages, but still to be considered. So they suggest you look at a time percentage of 0.01% of the time on that. And what that means is that you'll have two numbers. And actually, let me to kind of talk about this and put it in a numbers type thing. Let me do a path report. Pick something that's a little farther away here. So down here at the bottom, we've got a button for this path report. This is where it really shows kind of the meat of the calculations in terms of how did it arrive at the C over I ratio and all that. So what you've got is your reference path over here on the left and your existing path on the right. And these letters are the same as in that chart that I showed earlier. You've got D is your transmit site, E is the receive site, and that's for your proposed path, and then A and B are the transmit and receive for your existing. So it has, all the information, the coordinates and all this antenna information. It tells you the receive levels. And then when we get down here at the bottom is where we've got our interference analysis. So, here's where it's showing the discrimination attenuation in the angle, the free space loss that got calculated, the obstruction loss, which is the additional loss due to terrain. It shows the interfering signal level in dBm, and then down here our calculated C over I and our C over I objective, and then the difference between the two. So this obstruction loss, you'll notice we have 3.98, and so that's on the A column, so that's corresponding with from the A transmitter into our receive point at E. We've got 3.98 dB of attenuation on that interfering path. And if you look down here at below this, there's a little summary. It shows the long-term loss and the short-term loss. So when we're looking at 20% of the time, it sees that obstruction to be 45 dB, almost 46 dB. But when we dial that back and we look at 0.01% of the time, then that obstruction loss is only going to be 4 dB. So, there's a huge difference between the long-term and the short-term calculation. Now, one of the things it says in the TSV10F is that in the case where you're looking at the short-term fading, you should relax the C over I objective by 10 dB. So you'll notice here our C over I objective is listed as 55 dB. If you look at what's specified in the transmitter, it's going to show that as 65 because that's the long-term case, and that's what you specify there. When it analyzes the short-term, it's going to drop that by 10 dB. So it gives you a little bit of room to work with, but essentially when it runs the numbers and it figures out the margin, whichever case it's worse, that's what it's going to use. So when you see in our table the ST in and ST out, that's an indication that it's using this short-term case instead of the long-term case. If it doesn't show either of those, then you can assume it's using the long-term case. So that's just another little level of calculation that it does, and the program kind of does that for you, so you don't necessarily need to know about it, but it's important to understand because you kind of need to know that to understand how it's getting these numbers that it's using in the calculations. So essentially, yeah, but all these numbers that are specified up in here, you can use those to figure out, based on those formulas that I showed earlier on the slides, what your calculated C to I is, and then you're comparing that to the objective. So if you want to get into, if you're looking at a specific case and you say, I don't understand how it got that answer, this is the table you want to look at and try and figure that out. And like I say, it helps if you sometimes have a picture of that path setup that I had showed earlier to kind of give you an idea of what's going on. So that's essentially, what the program does and what it's showing you, and how you can analyze, a particular path and say, is this going to work or not, or what are the potential issues on this path. There are a number of other things that the program will do with this. I'm going to kind of run through these a little quickly because I'm looking at the time. I see where I managed to spend an hour thus far talking about this. So other things this will do, the show path layout button. This gives you an idea of the geometry. So whatever path you have selected in this list, it's going to show over here in this window. Now this first path is kind of interesting because we only see two things, and that's because our existing transmitter site and our proposed transmitter site are actually in the same place. So the interfering paths are actually right underneath these green ones. So the protected paths and the interfering paths are the same. This one's kind of a weird case where they've got essentially two transmitters on the same frequency but with different polarizations at the same location. When you crunch the C over I numbers, it says it shouldn't work, but apparently it might. The other was that? Oh, just just to show a more typical setup, you know, like here's something where so you've got D to E. It shows you this green path is your protected path. D is your proposed transmitter. E is your proposed receiver. A is your existing. That would be corresponding to whatever's in this row. A is the transmitter for that site, and B is the receiver. So you can kind of see what the geometry is, and you can see here that this interfering path is fairly long. And if you look up here at the top, you know, D to B, distance D to B, 50.4 kilometers. So this is kind of where you can get in and get to more how's it doing the calculations. This is also where you can go in and look at the terrain profiles. So for example, we want to look at our D to B path is essentially our interfering path. You know, this is where we're causing them interference. If you click on interfering DB, we can click on that and it will show us a terrain profile. So you see here there is some terrain blockage, but it's not, you know, it's not negligible, it's not a lot, but you'll see it actually shows an obstruction loss up at the top of this, -1 dB. And then in parentheses it shows that's using the 0.01% fading thing. So in this case, it ran the calculations for both the long term and the short term, and it determined that short term was the worst case scenario, and so that's what it's using. And so it will show you that there's some more things you can do with this as far as, you know, this window you can resize it and do different things. The edit settings, you can go in and play with that. I'm not going to go into a lot of details on that right now, but you can set how this looks quite a bit. And then this hard copy button is worth mentioning. This takes you into a special hard copy window where you can select, you know, what information you want to show on here. And if you hit OK, it's going to pull this up, and it gives you sort of a WYSIWYG type window that shows you all this information, and you can go in here and add, you know, a title or whatever information you want to put on it, and then print this out. So it's sort of a, you know, it's a page style thing for making a nice, you know, if you're trying to demonstrate to someone what's going on this path, you can use this to make a nice printout doing that. So, and the last option is to save graphic. You can just save this to a bitmap type file. So that's our path layout. One of the things that's new in AMPRO 2 is the ability to do mapping. In AMPRO 1, that path layout was about all you got, but on this, if you want to actually see on a map, you know, where these paths are, you can do that now. And to do that, you use this map menu. You can say show map. We'll open up the mapping window. And here we've got a bunch of paths. I'm going to go ahead and turn some of this stuff off so we can get a clearer view of what's going on. So we've still got a mess of paths here. This is just showing the individual paths themselves. If you go up here to map and you say edit plot settings, you can actually set, you know, the colors and the characteristics for each one, and down here at the bottom here it has a check mark to plot the interfering paths as well. And I've got those set up to be in dashed lines. So if we turn that on and then go back to our map, we actually can see now we've got all the interfering paths plotted as well. Now this map is kind of a mess in terms of all the paths on there, and probably in this situation you wouldn't want to look at all these. You'd just be concerned with one or two of the particular things. So these check boxes that you see in this table kind of define what paths are shown on the map. And if you go on the map menu, there's a select all and select none option. So if we go ahead and select none, that's going to turn everything off, and it just shows here's our reference path that we had put in. So now if we want to show, you know, one of these other paths on here, we can click that and it will show a reference path and then the interfering path. So you can use that to get an idea of, I'll zoom in on that so we can see it closer. And that gives us an idea of, you know, where is this path that we're interfering with, and you can work with it on that level. You know, of course, you can print this out and do things with it. One of the other things I will note about this, I'm going to turn a few more of these on, just kind of randomly pick some. When you click on one of the paths on the map, if you click on the reference, you know, it'll highlight it in black, but that's all it does. If you click on any of the red paths, which are the paths that we're protecting or being protected from, I guess. You can click on those, and when you do that, it will go up here and select that path in the table. So, if you're looking at the map and you want to, well, what's the deal with this path? If you click on that, then it's going to select that up in the table. So that, gives you a view, and here it scrolled down. So this one actually was not at the top, but it scrolled down when we selected it. But that's kind of a quick thing that you can do with the map. If you're familiar with Probe at all, if you click on map features, it's got all sort of the same types of settings. You can set all the colors and line widths and all that stuff. So there's a lot of similarity in the mapping there. There's a menu thing here where you can get into the map layout. This is sort of the page style layout. If you want to change that, you can do that. There's also fit map size to window. That will actually resize this to match the window. If you're in the graphic mode for layout, that kind of helps. And then there's an add to map option too. Like here, you can pick scale, and it'll put, down here in the corner, puts a little map scale for you. And then, of course, print map is the last option on there. So that's the quick version of the mapping thing. If you hit Edit Project down here, that's going to bring us to our Edit Project settings. This is where we can kind of change into these settings that we talked about. And like, for example, the Edit Propagation settings, I wanted to come back to this. So the way this works is up at the top, you pick the propagation model that you want to use. And this is another thing that's new in Microwave Pro 2, is that in Microwave Pro 1, it supported Longley Rice and this FMPTP model. We've now implemented this NSMA model, which is it's sort of a TechNote 101 based model, but it has some differences. And this is what is used by most of the frequency coordinators out there, I think. So if you want to get numbers, if the goal is to get numbers that match what everybody else is doing, which generally it is, that's sort of the recommended thing to use now, is this NSMA model. And then you can set the settings, for protected paths. You can set the % time and then the K factor used in the profile generation. And then it also has a switch for this 95% confidence factor. And then you specify your long-term and your short-term fading options. And you can change all these. And if you change them, say you're playing around, say you go to 10% time instead of 20 and you run your study, and you want to go back to the defaults or how the standard sort of TSB10F configuration is, there's a button up here at the top that says Set to TSB10F Recommended Values. If you click on that, it's going to select the NSMA model and set this up. If you want to set up the parameters for the other models, you can click on this Longley Rice tab. It has, similar settings that you can put in here. And then this FMPTP doesn't actually have any real settings, but that's a model you can use, but I don't really recommend it. I think for this, you're probably better off with Longley Rice or the NSMA. And so this is where you set all the settings, but it's whatever's selected up here at the top is what it's going to use. So if that's set on NSMA, it's going to ignore the Longley Rice and the FMPTP settings. If it's set on Longley Rice, it's going to ignore the NSMA. At the bottom here, there's an option for most conservative. Now, if you have it in that mode, it's going to do the calculations using all three models and then pick the value from whichever one is the most conservative. So if you were trying to be ultra conservative, you could put it on that, and that will run all the models, and then whatever depending on whether it's an interfering path or a protected path or what the situation is, it'll use the most, either the highest or the lowest number, depending on what's most conservative in terms of showing the most amount of interference. So that's how you can set up the propagation settings. And the rest of these are just options that were on that first window that I already talked about. So if you wanted to change one of these options without running a new study, you can do that. The one thing I will note, if you want to change the frequency of your reference station, and if you want to change anything about your reference station, you can use this edit button up here at the top. Say we wanted to change the EIRP, we could put that in there and it would do that. If you want to change the frequency, currently you will need to rerun the study or run a new study. You can't, if you just change the frequency, it's not going to refresh from the database and load in the new channels. It's just going to keep what was in here. So, and it gives you a warning about that if you try and do it. If you go in here and say, change that to 950 or something, and you say okay. It's going to say, notice the frequency has been changed. The program's not going to reload the database, so you know, you don't want to do that. And then it's got, it says this may invalidate the C over I objectives. Do you want to recalculate them? No. So actually, and this is going to go ahead and recalculate it, but all our results now are not necessarily going to be meaningful because we didn't reload from the database. So that's just something to be aware of, I guess. And we can go back in and reload that, but it doesn't have our transmit, but that's okay. We don't need to go and put all those in. So essentially, that's how it works and how you would analyze a single path. Now, getting into frequency searches, that is essentially just running a whole bunch of these individual one-way things. The last thing I want to talk about on this window, actually, though, before we get into that, is the address list. And that is when it comes time to do the PCN letters and such, you're going to send out letters. If you click on this address list button down here at the bottom, we've got some different options for what we can do. This human readable text report just basically gives you a list of all the addresses in the study. Generate a CSV is kind of the same thing, but it's in a CSV type format. And then down here at the bottom is sort of a newer way to do it, which is this coordination entity report, where it will kind of, the top two options it gives you for every row that you have in this table, it's going to generate an output. But it's very possible that several of the paths that are in this are owned by the same people. So instead of sending them, say 5 paths are owned by the same people, instead of sending them 5 letters, if you use this coordination entity, it will look at that and just list them once. So that's sort of the better way to go about this. And there's some options here. You can have a human readable address list. You can have a CSV address list. And so the thing with the CSV is you can bring that into Word and do a mail merge or whatever, or print labels with it. And that's kind of how you can get into that. There's an option to show the licensee contract and with address, and then you include the licensee contact in the CSV. If you don't, it just includes the licensee. So if I hit OK on this, just to show you what it gives us, since I asked for the human readable report, that's what it's generating here. So it generates 2 text windows, actually, one with the CSV file. So this is the thing, you could save this and import it into Excel or Word or whatever you're using for that. And it's got headers for the thing, so you can tell what's in their address lines. And then it also has this entity list, which this is what you'll see when the FCC wants to know who you sent letters to. This is the list of all the people that you sent letters to. And then down here after this was an option for the human readable thing. It just shows addresses for each contact. It has the contact name and then the address and the phone number and the email and all that. So that's the last thing that you might want to do out of here. To do, so I'm going to say new, I'm not going to say that, say frequency search. So when you do a frequency search, it essentially starts the same way. You have a window here where you put in your reference path. You're going to know your transmit and receive points and all that. At this point, you may want to put in a frequency that's in the band that you're working with, but it doesn't matter because it's going to overwrite that later. But so it's the frequency and the polarization are going to get changed later, but the rest of this stuff is what it'll use when it goes through and runs the thing. So I'm just going to hit cancel on this for a second to get to, here's sort of our main frequency search window. Now, since I canceled this, this didn't fill any of this stuff in actually. Let me go in and I'll pull something in and hit OK. Well, in this case, okay, so here's our reference station. The reference EM designator, like as I said before, that's important. You got to get that right. And then polarization to consider. There's H and there's V. So if you just wanted to only look at horizontal, you can pick H. If you just want to look at vertical, you can pick V. Or if you want to do both, you can do both. There's essentially 3 modes in Microwave Pro 2 that you can use to to look at. One is the step mode, which is essentially you just give it a start frequency, a stop frequency, and then an increment, and it will run a single path analysis like we just got done looking at for each one of those frequencies, and then give you a table that you can sort and figure out which one's going to work best. The other options are you can do a list, which is where you would enter a list of frequencies to consider. And then there's also a list for two-way paths. If you're working on a two-way path, you can load those in. And like on our one-way, on our list type ones, we actually have a library. There's some predefined files. So like if you hit the library here, you'll see it comes up with our cars frequencies. And the reason it does it, those are not necessarily evenly spaced, and there's some gaps and things in there. So those don't work out very well as a step type of thing. So when you load one of these, I'll say OK, then it just pulls in all the frequencies in that particular cars band. And then for the two-way, it's going to have two frequencies, you know, the forward and return frequency. It copied this stuff over from our one-way list and set the second one to something else. So I'll just show you. I'm just going to pull one of these up. So the way this goes, it has the band, and then it has your channel bandwidth. So you kind of pick which band you want in and which channel bandwidth you want to use, and then hit OK, and it will load in all of the forward and return frequency pairs. And occasionally, some of these, it has a notes section. Some of them will have a note where they're, you know, situations where there'll be certain frequencies that are reserved for certain things, or you know, ones that you're only supposed to use if you can't find anything else, type of thing. So the notes on some of these will indicate that. And then the rest of the options on here are exactly the same as on our single path thing, because that's essentially what it's doing. It's doing a bunch of single path analysis, and it's going to group these together. So with that, I think Doug had a couple of example type frequency searches that he was going to talk about. So Doug, if you're ready, I'll go ahead and turn that over to you, and you can.
Okay, John, very good.
Okay.
We'll get it over to me for just a moment. We're running quite late, so I just wanted to give you an example of the Microwave Pro. Is this up on the screen, John?
1 second here.
All right. All right. Show my screen. Here we go. Now it should be up on the screen.
All right. Yep.
All right, I just wanted to show you an example here of an actual frequency search. This was for the 950 megahertz band, and I'm not going to go through the search, but actually I've got one channel here that looked pretty good to me, but let's go over and look at the kind of thing you're going to see when you finish the search.
Yeah,
and here we have...
Sorry, let me interrupt 1 second here just to say that, so, you know, you guys kind of saw how long it took to do a single path analysis. It was, you know, 20, 30 seconds, somewhere in there. And so with these, because you're analyzing a bunch of different frequencies, they can take several minutes. So we want to spare you guys having to watch it churn for 5 minutes. And so we're just going to directly loading. But anyhow, all right, continue.
Right. Very good. So anyway, if you look at this, you can see that 944 looks pretty good. It has 0 incoming, and it looks like it has 1 outgoing problem. So, well, let's look at what the problem is and how serious it is. And this is the frequency 944, and you can see right up here we have an outgoing of minus 4.7. Generally, I consider outgoing more seriously than I consider incoming interference. Because incoming interference, it's something you're going to be caused, and maybe you can deal with that. But outgoing, you're causing it to your neighbor, and your neighbor may not be very happy. So basically what I would do in this particular case is look in here to see what kind of antenna we're using on both ends of these of the path here. And looks like we're using the MF950B for the transmit, and the receive antenna is a generic receive antenna. So we can do one of the two things. We can change the transmit antenna to something with a little narrower bandwidth. This has a bandwidth here of 16 degrees, which is quite wide, and we may be able to reduce the interference caused or we can go in and change the receiver. Well, that receiver antenna is their antenna, and they might not be too willing to do that. So what I'm going to do is go into the library and very quickly show you that we have to choose a 950 megahertz antenna. And so how do you tell what is 9 megahertz? Well, generally these are listed with the megahertz indication coming up second. So if you choose this 13, you can see this, let me see, I'll use one here. This is 25 megahertz, FP10. 10 is approximately the gain usually of this antenna. And so we can see here that we're going to be in that mid-range, but that's not what we want. Just to move along here, I think we'll use one of the Catherine Scala antennas. And here's a 950, and I think I'll choose the 950B, and it's obviously in the right bandwidth, and we'll choose that. And then you can choose, you select your beam width, and I'm going to select the beam width from the VV, and here's what we'll get here. We'll have to do a little recalculation, and we'll see what happens to that margin on the output. And just about done here. And it didn't change it. Okay. Not sure why it didn't change it. We might have had a generic antenna that looked quite the same. So at this point, that's the idea. You get it. You might have to play around with these patterns and the antennas to see which one would take care of the issue that you're having with outgoing interference, and the same thing with incoming interference. So right now I think we should go, because we're still running quite late, to questions. And I see Michael Brown says you use the mini flictor, and that's probably why. So I could probably go back and use the standard. Let's see here. I'll go back to the edit the path here and use the standard transmit, and we want the mini flictor. Yeah, that looks a lot better. Let's see if that makes a change. Well, it dropped it a little bit, but not a lot. So, but you get the idea, and I think this is an actual frequency that we used, so I think you can make it work by manipulating the antenna patterns. All right, so are there other questions out there? John is still here on the line, and I'm here, and we can answer those questions if you have them. I found John's presentation to be very complete, and we certainly, every time I watch John explain the program to me, I learn a lot. So I'm just a user, and John is the master programmer for this particular program. So I don't see any other questions up there. I'm still looking for those questions. You see something that you've missed that you're not sure of? We can spend a little bit more time on that. All right, still don't see any questions in the chat box. We do have your mics off, so we could turn those on, I suppose. Might make it easier. But well, I think for now, because we don't see any more questions, we will conclude the webinar for this afternoon. And we'd like to thank all of the attendees for tuning us in and looking through. If you have some questions after this is over, please email us and let us know. We'd be happy to answer the questions to the best of our ability. And otherwise, thank you very much. And for John and I, we'll say goodbye.